Good morning, dear colleagues, participants, guests. Now we start our two section. Dear colleagues, it's my pleasure to open this section dedicated to modern electronical and energy system. And our first speakers today are Vitaly Klivda, Olga Sakhno, Konstantin Kornilenko, Dmitry Mizulov, and Evgen Medvedev. With the presentation, decarbonization of road transport by using hybrid electric vehicles. Let me share my screen.
Good afternoon, dear colleagues. Thank you for the opportunity to present our study entitled Decarbonization of Road Transport by Using Hybrid Electric Vehicles. In this work, we proposed a physically interpretable mathematical model for assessing how hybrid electric vehicles can reduce fuel consumption and carbon dioxide emissions under realistic driving conditions, with particular attention to urban operation. The problem is highly relevant because the transport sector remains one of the major contributors to global greenhouse gas emissions. According to the background used in the study, transport accounts for about 24% of global CO2 emissions, and more than 45% of transport emissions come from the passenger cars. This makes decarbonization of road transport a priority, especially in urban environments where traffic density, stop-and-go operation, and energy losses are most pronounced. Traditional internal combustion engine vehicles are still dominant, but they have relatively low energy efficiency and high specific emissions. Therefore, an intermediate technological solution is needed before the full transition to zero-emission mobility becomes realistic. Hybrid electric vehicles are important because they combine the advantages of conventional and electric propulsion. They reduce fuel consumption, enable regenerative braking, and provide more flexible energy management, without requiring a fully developed charging infrastructure. However, the key point is that the benefit of hybridization is not automatic. It depends on how effectively energy is distributed between the internal combustion engine and the electric motor under changing driving conditions. So, the engineering problem is not only the presence of two power sources, but the optimization of their interaction. The objective of this study was to develop a mathematical model for evaluating the energy efficiency and CO2 emission reduction of hybrid electric vehicles. The methodological core of the work is the use of the second-order Lagrange equations, which allow the hybrid powertrain to be represented as a coupled mechanical electrical system. In this framework, we account for kinetic and potential energy, generalized forces, and dissipative losses with one analytic space. This is important because it provides a physically grounded description of the interaction between the internal combustion engine, the electric motor, and the vehicle motion. The main novelty is the combination of classical Lagrange dynamics with power balance analysis and realistic driving cycle data, including the Ukrainian urban cycle. At the center of the model is the hybrid vehicle power balances equation, as you see, where the wheel power is determined by the contributions of the internal combustion engine and the electric motor, minus system losses. To describe power sharing, the study introduced a torque distribution coefficient, as named lambda, which reflects what part of the traction effort is provided by the electric motor relative to the total torque. The optimization goal is to minimize total energy consumption over the driving cycle while preserving the required vehicle dynamics. The second key component is the modeling of the regenerative braking, where part of the kinetic energy is returned to the system. In the reported results, the recovery coefficient under urban conditions is about 0.22 to 0.27, which is one of the major contributors to improved fuel economy. The simulation was implemented in MATLAB and Simulink with a time step of 0.1 seconds. The model was calibrated using road test information and published data. Three representative production hybrid vehicles were selected. As you see, Toyota Prius 4, Hyundai Ioniq Hybrid, and Honda Insight. These models reflect different hybrid electric vehicles architectures and therefore improve their generalizability of the conclusions. An important point is that the analysis considers not only standard cycles such as worldwide harmonized light vehicles test procedure, but also the Ukrainian urban cycle, because local traffic conditions can substantially affect both efficiency and emissions. Here we see the dynamic behavior of the hybrid system. On the first picture, you can see how power is distributed over time. At low speeds up to roughly 30 km per hour, the electric mode dominates. In the medium range, approximately 30 to 80 km per hour, the vehicle operates in mixed mode, where the electric motor supports the engine and smooths transient loads. At higher speeds, the mechanical drive becomes more dominant, while the electric machine can operate in generator mode during deceleration. The second graph shows the dependence of carbon dioxide emissions on speed. The most favorable operating zone is around 40 to 60 km per hour, where the hybrid system reaches high efficiency and low emissions. At very low speed and high speed, emission increase due to the stop-and-go losses and higher power demand. Compared with conventional internal combustion engine vehicles, the hybrid vehicles in the study reduced fuel consumption from 6.7 to 3.9 liters per 100 kilometers. CO2 emissions decreased from 152 to 88 grams per kilometer. The total efficiency increased from 27% to 39%, which means an increase of 12 percentage points, or about 44% in relative terms. Energy consumption also decreased substantially from 65.4 to 38.5 kilowatt hour per 100 kilometer, and the economic cost of mileage fell from 0.083 to 0.054. It is both technically significant and the economically relevant. The practical significance of the study is threefold. First, the model
Dear colleagues, we have some issues with internet connection. Do you hear us now?
Yes, we can hear you.
Thank you. Thank you. Thank you for your presentation. I have some question. Sorry, stop. There are any questions for the speakers in the audience? Please. Tell me, please, how sensitive are results of your model to real-world uncertainty, such as driver behavior, road gradient, and traffic variability? And how does this affect the accuracy of CO2 emission predictions?
Very interesting question about sensitive analysis. The Lagrange-based model is sensitive. Our model is sensitive to driver behavior. Also sensitive to road gradient and traffic variability. These factors affects the main energy terms of the Lagrange function, such as acceleration and braking, potential energy of slopes, traction power, and resistant forces. These factors influence to CO2, carbon dioxide emission predictions through the model inputs, but do not change the model structure. Compression with empirical data showed a deviation of about near 5%. It's a result of our experiment.
Thank you. Thank you. I have a question. I would like to ask you about considering the rapid development of battery electric vehicles. How do you value the long-term relevance of health as an intermediate solution in decarbonization strategies, especially in terms of total life cycle emissions?
Thank you. Thank you. It's a second good, interesting question about our hybrid electric vehicles. Health, as you know, should be considered as transitional, but not final as a decarbonization technology. About battery electric vehicles are preferable in long term, but their life cycle benefits depend to clean electricity, charging infrastructure as known, and battery production impacts. In countries with fossil-based electricity or limited charging infrastructure, HEVs can provide immediate CO2 reduction using existing infrastructure. The smaller batteries also reduce demand for critical materials.
Thank you for your answer. Let's introduce next speakers.
Thank you.
Next presentation, decarbonization of road transport by using hybrid electrical vehicles. Sorry. Next presentation by Mikhailo Kosor, Dmitro Danilchenko, and Andriy Sinetsky, development of mathematical circuit field model for complex electromechanical systems with pulse regulation.
Good afternoon. I'm glad to welcome everyone to the conference. My topic of the presentation is the development of a mathematical circuit field model for complex electromechanical system with pulse regulation. Speaker Mikhailo Kotsur. Despite the high energy efficiency and accuracy of a modern electromechanical system with variable frequency control, the use of frequency converters has a number of significant limitations regarding the application in high voltage, powerful electric drives for industrial installations. One of the main reasons with variable frequency control is limited to the high voltage EMS is the high cost resulting for the complexes design of high voltage frequency converter. To ensure the energy efficient operation of high voltage EMS based on the induction motor, a pulse control system in the rectifier rotor current socket exists. Due to the lower voltage of the rotor sides of the induction motor, the use of semiconductor elements of the induction motor rotor side will significantly reduce the cost and increase the efficiency of the converter for a high voltage EMS. Therefore, to determine the optimized parameters of such system and the optimal control algorithm for achieving optimal energy efficiency indicators, there is a necessity to develop improved methods for mathematical modeling of electromagnetic and electromechanical processes for such EMS. The aim of the work is to develop a mathematical circuit field model of the EMS with the pulse regulation of induction motor rotor's rotational speed. This model should allow for the combination of electromagnetic and electromechanical processes between the circuit and field part of the EMS model. Also, it will allow for the inclusion of the geometric features of the active part of the induction motor with socket realization and the commutation of its windings with elements of traditional power supply systems, as well as the structural element of a pulse converter in the rectified rotor current socket. When constructing the two-dimensional field part of the EMF model of the active section of a high voltage wound rotor induction motor, certain assumptions and conditions are avoided with are not taken into account during the model processes. The following structural components of induction motor are included: the starter, housing, bearing shields, front and rear covers, outer casing, cooling fan, shaft, and other similar parts. The electromagnetic fields is assumed not to propagate beyond the boundaries of the active section of induction motor. The limitation of magnetic core of induction motor is not taken into account. The conditions that displacement current and free charge are absent is adopted. The condition that the electromagnetic properties of the ferromagnetic materials are isotropic is adopted. The manufacturing tolerance of the winding production of the starter and rotor of induction motor is ignored. They are assumed to be idly placed in the slots, and the projection lengths of the end windings are equal. The geometric model of induction motor with constructive elements of represented by cross-section active sections and shown in figure 1. The mathematical description of the transient electromagnetic processes for the overall computational domain of the active section of induction motor is represented by a system of first-order partial differential equation is used with help number 1. With realization rotational computational domain of rotor of the induction motor was used equation number 2. In two-dimensional field model, the magnetic field is considered plane parallel. Therefore, the projection of the magnetic vector potential, the resultant magnetic flux density and magnetic field strength vectors, as well as the electric potentials at the start and of the slot area of the starter and the rotor winding coil section will be determined with help equation number 3. On the external boundaries of the spatial domain of the geometric model, as well as the separate model of starter and the rotor of induction motor, uniform boundary conditions are set in accordance with help equation number 4, and coupling conditions of magnetic and electric fields with help equation number 5. To enable the rotation of induction motor during the field calculation processes, the system of equation of the mathematical model was supplemented with the rotor angular velocity equations and the electromagnetic torque equation with help number 6. The socket part of the EMS accounts for the socket implementation of the coil connections for both the starter windings and the rotor windings of induction motor. Since the slot part of the starter and rotor windings coil section are elements of the field model, their end windings are represented as RL elements in the socket part of the model. Schematic implementation of the connection of the induction motor windings in the socket part of the model shown in figure 2. To account for the interconnected electromagnetic processes between the socket and field part of the model in the induction motor's active section when the starter windings is supplied from conventional power sources, we supplemented the mathematical model of the electromagnetic field with a system of first-order differential equation which ensures the interconnection of the magnetic circuit of induction motor active part and the electric circuit of its starter with the active resistance and inductance of the starter and the rotor windings are parameters of the electromagnetic field. Therefore, these parameters for the circuit part of the model were determined with using equation up 9 to 12. To implement a complete model of electromechanical converter with pulse regulation in the rotor circuit, the schematic part of the induction motor model was supplemented with the schematic model of the pulse converter. The terminals of the phases of the rotor windings are connected to a semiconductor converter, which is a serial connected uncontrolled three-phase rectifiers, a boost type pulse converter, and an inverter node to the network. The uncontrolled three-phase rectifier and inverter node to the network provide respectively a connection between the AC and DC circuits. Schematic and geometric interpretation of the circuit field model of EMS with pulse regulation shown in figure 3. Depending on the state of the power switch, we will consider the features of accounting of the interconnected electromagnetic processes between the circuit and field part of the model in the active section of induction of the induction motor rotor. In this case, the mathematical model of the electromagnetic field, taking into account the equation for interconnected electromagnetic processes between the circuit and field part of the model in the induction motor starter active section, must be supplemented with system of first order differential equation which ensure the interconnection of the magnetic circuit of the induction motor active section and the electric circuit of its rotor windings with consideration of the converter operation. For the case then the power switch is closed, the system of equation describes the electromagnetic processes will have the following form. For a C rotor circuit, we used equation number 13, and for the DC rotor circuit we use equation number 14. Let us consider the case then the power switch is in the open state. In this case, the system of equation describes the electromagnetic processes will have the following form. For the AC rotor circuit, we used equation number 15, and for the DC rotor circuits, we used equation number 6. This is the schematic realization of the starter and rotor windings and the pulse converter in the induction motor rotor's DC circuit, as well as the joint solution of the system of equation dependent on the state of the impulse converter's power switch were performed to use the console multiphysics software. This was achieved by employing the FEM and time-stepping integration methods utilizing various multiphysics structures with the rotation machinery and magnetic and electrical circuit interfaces. Feature 4 shows the results of the field calculation for induction motor. During the circuit field modeling of the EMS with pulse regulation in the sub-synchronous speed range of the rotor with these parameters. Just results for this work. A new hybrid modeling approach is proposed for the transient electrophysical processes of ACEMS, which allows for the combination of special elements of the electromagnetic fields with local or unit elements of the electric circuit. Next, following the developed methodology, coupled mathematical circuit field model of the EMS with pulse regulation of the induction motor rotational speed was developed. It allows for the combination of electromagnetic and electromechanical processes between the circuit and field part of the model, and ensures the integration of the specific geometric structure of the induction motor active section with the schematic realization and commutation of the windings, improving elements of traditional power supply systems and the structural elements of the pulse converter. The next results, the application of the developed mathematical circuit field model of the EMS with pulse regulation will allow for higher accuracy, detailed resolution, and convergence of the electrophysical processes within the structural elements of the EMS during further investigation of the EMS with pulse regulation in its quasi-transient operating modes. And the last results, the proposed methodology exhibits higher versatility and can be extended to various classes of electromechanical systems. Thank you for attention. Good afternoon. I'm glad to welcome.
Olena, do you have a question?
Yes, hello to everyone. I want to ask about how does the proposed hybrid circuit field approach affect the accuracy and computational efficiency of modeling transient electrophysical processes compared to classical methods, purely circuit or field?
Thank you for question. It's a good question. Therefore, the accuracy of the simulation of the proposed hybrid circuit field model will not be lower if all components of the electromechanical system with a pulse converter were considered only in the paradigm of field problem. Conversely, the accuracy of this class of model is significantly higher compared to circuit model due to the full consideration of design features, electrophysical and electromagnetical properties of the material, and so on and so forth. However, the computational efficiency of the hybrid circuit field model will not be higher than that of the field submodel of the electromechanical converters, but will be much lower compared to the socket model, since each iteration step will depend on the convergence of the equation described the sum field model. However, despite the worse computational efficiency of the hybrid socket field model compared to socket models, hybrid models allow taking into account most non-linearity some effects. That's all.
Thank you.
Thank you for answer.
Thank you. Dmitro Kulagin, please. Your question.
Thanks. I have one more question. What are the limitations and prospects for the developed mathematical model or for application to other classes of electromechanical systems with different geometries and control type?
Thank you, Dmitro. This is good question. It's a needed question. I think some proposed methodology for synthesizing mathematical models that describes electrophysical processes at the micro and macro levels can be applied to any existing classes of electromechanical systems, as well as a little studies classes of electromechanical systems. The main task of scaling electromagnetic processes in separately selected final elements of a complex model of electromechanical systems is the study of complex transient processes and the identification of electrophysical effects, phenomena. The limitation is using this approach may be the computing resources of the personal computer and the calculation time. As for the application of this approach for modeling electromagnetic processes of electromechanical systems in quasi-transient modes of its operates, this depends on the feasibility which is determined by the researcher.
Thanks.
Are any other questions in audience? Okay, thank you, Mikhailo. Next presentation, research and development of methods for ensuring static stability in specialized synchronous electric drive by Volodymyr Zinovkin, Yuri Krisan, Mykola Antonov, Andrei Pirozhok, and Andrei Luchko. Just a moment, please.
Dear participants of the conference, let me introduce to your attention the report on the topic Research and Development of Methods for Ensuring Static Stability in Specialized Synchronous Electric Drive. A new direction in optimizing control systems for multi-parameter technical objects is evolving within the global scientific and engineering community. This trend is driven by the fact that existing automated systems primarily rely on standard linear control laws, which encounter difficulties in mathematical modeling. Such laws do not always satisfy the requirements of real-world technical objects and lack robustness, often leading to deviations from the prescribed objectives of the technological process. The optimization of control systems for multi-parameter objects is characterized by the simplicity of ongoing analysis and synthesis, combined with robustness and reduced precision requirements. A combined functional M is formulated as the optimality criterion, integrating several performance indicators, such as time and energy or speed and power. This approach simplifies the initial problem. For instance, the application of Euler's dynamic equations is reduced to a combined optimal control problem for a technical object. This combined problem incorporates a single supplementary scalar differential equation that defines the path to optimality. It differs from ideal control by its simplicity while maintaining quality indicators sufficient for practical application. A multi-parameter optimal. The induction furnace is powered by a high-frequency synchronous generator, which, together with an induction motor, constitutes a specialized electric drive. Compliance with the furnace's technological process directive objective is achieved through reactive power compensation and the adjustment of factors leading to the loss of the synchronous machine's static stability, as detailed in the table on slide 3. As an example, fragments of the consequences of an emergency failure of a synchronous generator are presented on slide 4. Fragment of stator winding damage A and mechanical damage to the rotor teeth B, resulting from prolonged violations of the generator's static stability. The objective of this study is the synthesis of novel mathematical frameworks and computer simulations that ensure the static stability of high-frequency generators through integrated multiparametric optimization. The research hypothesis proposes a combined multiparametric control system that ensures the maintenance of the machine's static stability within optimal limits while providing sufficient response speed. The scientific novelty of the work lies in the development of new mathematical and computer models for ensuring the static stability of a high-frequency generator through the implementation of multiparametric optimal control. This approach allows for a reduction in the influence of external factors and ensures the directive technological loading of the furnace based on modern microprocessor-based and software automation tools. To ensure the reliable operation of a synchronous generator, it is necessary to maintain static stability conditions by mitigating a number of adverse factors, the primary of which were listed in the table on slide 3. This challenge is addressed through the development of a mathematical model. The torque of the magnetic leakage field depends on the current position of the rotor of the synchronous machine and the current in the stator windings, equation 1, where U, 1m, and omega 1 are the amplitude and rotational frequency of the voltage applied to the stator, and alpha 1 is the initial phase of the voltage U1. In the synchronous mode of the machine, the electromagnetic torque on the rotor shaft depends on the derivative of the mutual inductance of the stator and rotor windings, L12, as well as the rotation angle of the rotor relative to the stator, equation 2. Under synchronous EMF conditions, the requirements of equation 3 are satisfied. The dynamics of electromagnetic and electromechanical processes correspond to the external power angle characteristic shown in figure A. The conditions for ensuring the static stability of the machine are presented in figure B. The electromechanical transient process under small deviations satisfies equation 4. By expanding the function into a Taylor series for sufficiently small values of perturbation and retaining only the zeroth and first order approximations, we arrive at equation 5. Here, the variables represent the power variation limits during angular deviations of Pm delta delta. For the investigation of the electromechanical transient process, a system of 2 equations with 5 unknowns was obtained. To achieve an optimal solution for the mathematical stability model, it is necessary to supplement this with 3 more equations. The same power value P is represented as functional dependencies on the EMFE and voltage U, equations 6 to 8. By substituting these values and performing elementary transformations, we obtain the 3 fundamental equations required for studying static stability, equation 9 to 11. Using the Hurwitz method for nth-order objects, the necessary and sufficient condition is the absence of aperiodic instability. This allowed for the construction of a multi-parameter mathematical system for ensuring the static stability of a synchronous generator in the following form, equation 12 and 13. The dynamics of the process are described by equation 14 and 15. The mathematical model of the synchronous generator's rotational frequency oscillations is presented on poster 10, equation 16, where delta omega is the rotor speed deviation from the synchronous speed, h is the rotor moment of inertia, T sub m is the mechanical torque, T sub e is the electromagnetic torque, K sub d is the damping coefficient, omega of t is the rotor speed, and omega sub 0 is the synchronous rotational speed. The block diagram of the simulation model for the optimal control system and the transient processes in such a system are presented on slide 10. The functional diagram of the synchronous generator's computer model for static stability research is presented on slide 11. The results of the simulation of the synchronous generator's electromagnetic and electromechanical processes are also provided here. As a conclusions, the conditions for maintaining the static stability of a high-frequency synchronous generator under transient loading conditions are proposed. Based on these conditions, a multi-parametric mathematical model consisting of a nonlinear system of second-order differential equations has been developed. The effectiveness and practical application of these models have been verified through corresponding computer simulations. The simulation results demonstrate that electromagnetic and electromechanical processes change instantaneously under the influence of adverse factors, which affects the technical condition of the synchronous machine. Voltage level disturbances lead to overexcitation of the magnetic system, as well as mechanical vibrations of the synchronous generator shaft and the electric drive. In the absence of such disturbances, all processes stabilize and the loading mode complies with the directive target. This confirms the functionality of the developed mathematical and computer models, as well as the efficiency of their practical implementation. Thank you for your attention. Dear participants,
Any question in audience? Okay. Dmitro Kulagin, please.
I have one question, thanks. Why did you choose such a complex mathematical model, and can it work fast enough for real-time control?
Thank you for your question. The choice of such a model is determined by the need to simultaneously account for both electromagnetic and electromechanical transient processes. Because of model must consider changes in load angle, rotor speed, electromagnetic force variations, and transient in the excitation system. About can it work fast enough for real-time control? Yes. Thanks to modern microprocessor tools, this level of complexity doesn't cause critical delays.
Thank you.
Olena Nazarova, please.
Yes, explain please, can your control system also help predict equipment damage or only maintenance stability?
It's a very good question, thank you. It's more like not predict but prevent equipment damage. The proposed system not only maintains stability but also serves as a protective mechanism. The system minimizes mechanical shaft oscillations, which typically lead to fatigue crack in a rotor teeth. Since the system promptly responds to lower voltages, it prevents excessive heating of the winding, which is the primary cause of accelerated insulation aging.
Thank you, Olena. I have one question. Tell me, please, what type of excitation control system did you choose? Proportional or PID controller?
As I remember clear, it's PID.
Equation, just a moment, please. I find your equation. Equation 3 is for proportional excitation system.
Oh, sorry,
Not PID.
misunderstanding.
Thank you. Thank you. Next presentation, stabilization of the network frequency of a gas turbine power plant with a capacity of up to 10 megawatt using supercapacitors by Vitaly Slipchenko and Mikhailo Polyakov. Just a moment. I start presentation.
Good day, dear colleagues. My name is Vitaly Slipchenko from Zaporizhia Polytechnic National University. Today I would like to present our research titled Stabilization of the Network Frequency of a Gas Turbine Power Plants with a capacity of up to 10 megawatts using supercapacitors. This work is devoted to improving the dynamic characteristics of gas turbine power plants operating under transient disturbances. Gas turbine power plants with a capacity from 1 to 10 megawatts are widely used in distributed generation systems and industrial power supply. Such power plants are often applied in autonomous or weak electrical grids, where the stability of electrical parameters is especially important. In conventional gas turbine power plants, frequency regulation is performed by electromechanical fuel control systems. Although these systems provide reliable steady state operation, their dynamic response is limited due to mechanical inertia of the turbine and delays in fuel control actuators. As a result, during sudden load changes or electrical disturbances, the power balance is the system can be temporarily voided. This leads to significant frequency deviation, show recovery of nominal frequency and increased mechanical stress on the turbine shaft. Therefore, the main objective of this research is to improve the dynamic frequency response of a gas turbine power plant during transient disturbances. To achieve this objective, we propose integrating a supercapacitor energy storage system or SCESS into the electrical structure of the power plant. The supercapacitor system is intended to provide fast active power support during short-term disturbances. Such support allows compensation of temporary power imbalance and improves the dynamic stability of the power plant. As expected results, the use of supercapacitors should lead to reduction of frequency deviation, faster recovery of nominal frequency, and improved stability of the system. The scientific novelty of this research lies in a system-level investigation of fast active power support in gas turbine power plants. The study analyzes the interaction between the electromechanical turbine governor and a fast energy storage system based on supercapacitors. Particular attention is given to the influence of supercapacitors on frequency dynamics during severe transient disturbances. The key feature of the proposed approach is the supercapacitor of functions between two subsystems. The supercapacitor system provides instant electrical response, while the turbine control system gradually restores state operation. This combination allows improvement of the dynamic behavior of the power plant without modifying the mechanical control system. A gas turbine power plant model. To investigate the proposed approach, a simulation model of a gas turbine power plant was developed in the MATLAB Simulink environment. This studied power plant has a nominal electrical capacity of 2.5 megawatts and operated at a generator voltage of 6.3 kilovolts. The model includes the main components of a typical gas turbine power plant: gas turbine drive, synchronous generator, electromechanical fuel control system, and generalized load model. This electromechanical fuel control system regulates the mechanical power of the gas turbine depending on frequency deviations. However, due to the inertia of the turbine and delays in the actuators, the response speed of this control system is limited. To improve the dynamic characteristics of the power plant, a supercapacitor energy storage system was integrated into the electrical structure of the model. The supercapacitor system consists of a supercapacitor battery, a bidirectional DC-DC converter, a DC bus with a voltage of 1 kilovolt, and a grid-connected inverter. The total energy capacity of the capacitor system is 6.75 megajoules. The main purpose of this system is to provide fast exchange of active power with the electrical network during transient disturbances. When a power imbalance occurs, the supercapacitor system can instantly deliver or absorb power, which helps stabilize the frequency of the power plant. The control strategy of the supercapacitor system is based on frequency deviation of the generator. The reference active power of the supercapacitor system is proportional to the frequency deviation. If the system frequency decreases, the supercapacitor system injects active power into the network. If the frequency increases, the system absorbs excess power. In this way, the supercapacitor system provides fast compensation of power imbalance, while the turbine governor gradually restores steady-state conditions. To evaluate the effectiveness of the proposed system, two severe transient disturbances were simulated. The first disturbance is the direct start of an asynchronous motor with a power equal to 40% of the rated power of the plant. This mode causes a sudden increase in load and lead to noticeable frequency drop. The second disturbance is a three-phase short circuit on the 6.3 kilovolt AC bus. This event represents one of the most critical operating modes for frequency stability, as it causes a sharp imbalance between mechanical and electrical power. The simulation results show the dynamic behavior of the system during the short circuit event. During the fault, the starter current of the generator increases significantly. After the disturbance is cleared, the power plant enters a transient process. The integration of the supercapacitor system allows the system to respond more effectively to this disturbance. The results demonstrate that the use of the supercapacitor system significantly improves the dynamic behavior of the power plants. In particular, the maximum frequency deviation is reduced, the recovery time becomes shorter, and the amplitude of oscillations decreases. This leads to a reduction of mechanical stress on the turbine generator shaft. Conclusions. In this research, the dynamic characteristics of gas turbine power plant were analyzed with and without a supercapacitor energy storage system. The simulation results show that the supercapacitor system provides active power support during transient disturbances. As a result, the integration of supercapacitor system reduces frequency deviation, improves recovery time, and increases the overall dynamic stability of the power plant. Although the use of supercapacitor in power systems is not a new concept, they performed analysis of transient processes in typical startup and emergency operating modes, made it possible to refine the required parameters of the supercapacitor system and evaluate its influence on frequency stabilization of gas turbine power plants. Thank you for your attention. I will be happy to answer your questions.
Are there any questions in audience? Okay, I have a question. Tell me, please, how did you model supercapacitor in details?
Supercapacitor modeled by programmed source, three-phase programmable voltage source with modeling energy with limited energy.
And thank you. And how you control amount of energy injected to your system for stabilization?
I calculated it, and it was parameters that I for this model for three-phase programmable voltage source.
Okay, okay, thank you. Any other questions? Okay, thank you for participants. Now we have a technical break for 10 minutes and we will continue our work at 11:15.
Thank you.
Dear colleagues, we can continue. We begin our session 2 of section Modern Electrical and Energy Systems. We have 4 presentations in this session, and the first presentation is steam droplet power generation system with conical hydro turbine by Tatiana Mazur, Irina Vashichak, Sergei Vashichak, Miroslav Mazur, and Pavlo Prisязhnюк. One moment, please. I start presentation.
Good afternoon, dear conference participants. My name is Tatiana Mazur. I represent the Ivano-Frankivsk National Technical University of Oil and Gas. The topic of our research is steam droplet power generation system with a conical hydroturbine. This work was carried out by a team of authors, Irina Vashichak, Sergei Vashichak, Miroslav Mazur, and Pavlo Prisязhnюк. Allow me to present the main finding of our study. The relevance of this work stems from several important factors. First, the global energy crisis stimulates the development of efficient electricity generation technologies. Second, the destruction of critical energy infrastructure in Ukraine creates a strong demand for autonomous and compact backup power systems. Traditional solutions such as diesel generations and solar panels have important limitations, including full cost, environmental impact, noise, and dependence of weather conditions. The objectives of this research was to develop and experimentally validate a compact power generation system with a conical hydroturbine. The proposed design improves thermal to mechanical energy conversion by optimizing steam flow and reduction energy losses in a closed heat paper system. Sustainable electricity generation requires efficient thermal energy conversion systems. Biomass fuels such as wood and agricultural waste are promising for decentralized power production, while compact rocket stoves can serve as effective heat source for small-scale generation systems integrate with thermoelectric modules or steam turbines. However, exciting microsteam systems have several drawbacks: low conversion efficiency, below 5 or 10%, structural complexity, instability of conversion turbines in a high-speed steam flow, high manufacturing precision requirements, and large dimensions. Therefore, there is a need for a simple and aerodynamically optimized turbine capable of operating in a closed, low-pressure heat paper system. To solve these issues, we propose using a conical 6-blade ONIPCO-type hydroturbine integrate into a closed steam flow system. The design improves steam expression, reduces flow separation, and increases kinetic energy extraction efficiency. The system includes a rocket stove as a biomass heat source, a closed AISI 304 stainless steel vacuum heat paper, a conical ONIPCO-type hydroturbine, and 3-phase synchronous generator MaxRock G100S. The operating principle is simple. Water is heated, the working fluid evaporated under vacuum, steam rotates the turbine and drives the generator, producing electricity. The steam is then condensed and returned to the heating zone, completing the closed thermodynamic cycle. To evaluate the performance of the proposed power generation system, we developed a generalized mathematical model that combines all thermal and mechanical processes into a unified thermodynamic framework. The model describes the thermal power of the rocket stove depending on the type and mass of biomass fuel, heat losses due to radiation and convection, fuel thermal power transferred to the working fluid, steam mass, flow rate and steam velocity inside the heat pipe, and the mechanical power generated by the conical turbine. The total thermal power of the stove is determined by the full mass, calorific volume and furnace efficiency. This is different formula, different values. Using this thermodynamic model, calculations were performed for 9 different types of wood fuel, allowing a comparative analysis of system performance under different operation conditions. This slide presents the comparative calculation results of 9 different wood fuel types used in the proposed power generation system. The highest thermal performance was achieved using pine, spruce, and larch wood, which provided a total stove power of approximately 13.2 kilowatts and the shortest water heating time, about 4 to 2 seconds. Beech and oak also demonstrated heat performance with thermal power values ranging from 12.6 to 12.9 kilowatts. Beech and ash wood produced the highest radiation heat losses due to their elevated combustion temperatures, whereas older showed the lowest thermal losses. An important result is that for all investigated fuel types, the weight temperature reached 90 degrees Celsius is less than 7 minutes, while the useful absorbed thermal power exceeded 2 kilowatts. Experimental verification of the prototype confirmed the operability of the proposed system. The generator produced approximately 50 watts of electrical power at a turbine rotation speed of 380 revolutions per minute, with a heating temperature of 140 degrees Celsius and a cooling temperature of 10 degrees Celsius. This result demonstrates the feasibility of compact biomass-based steam droplet power generation using a conical hydroturbine. Modern steam droplet power generation system based on heat pipes often suffer from complex design, high manufacturing cost, low efficiency, and limited sustainability for field and winter conditions. To overcome this limitation, a simple and reliable steam droplet power generation system with a conical hydroturbine was proposed for autonomous operating. The system used distillate water as the working fluid inside a closed evacuated heat paper. The lower section of the paper is heated by hot water, causing the fluid to evaporate under vacuum. The generated vapor moves through the insulated paper section toward a 6-blade conical turbine based on the Onipko rotor principle, ensuring smooth start-up and efficient energy extraction. The turbine drives a generator that produces alternating current. An oil layer prevents evaporation of distillate water in the result section of the pipe. After passing through the turbine, the vapor is cooled in a coil with circulation cold water, condenses in a capillary mesh, and returns to the low section of the heat paper, completing the closed cycle. The mesh also prevents oil from entering the hot vapor channel. A mathematical framework was developed to calculate the main parameters and evaluate the thermodynamic and energy characteristics of the proposed system. Analysis of the data in table produced the results shown in Fig 3 or 6. Fig 3 indicates that the shortest water heating time, about 4 to 2 seconds, was achieved using pine, spruce, and larch due to their high calorific volume and low heat losses, Longer heating times, around 4, 5, 6 seconds, were observed for maple, beech, and alder. According to Figure 4, the maximum thermal power of approximately 3.2 kilowatt was also obtained for pine, spruce, and lodge, confirming their high energy efficiency. Beech and oak showed a slightly low value of 12.6, 12.9 kilowatt. Fig 5 demonstrates that the highest radiation and convection losses occurred for beech and ash, while alder had the lowest heat losses. Fig 6 shows the maple achieved the highest combustion temperature, about 1200 degrees Celsius, whereas alder had the lowest. Overall, system performance strongly depend on biomass fuel type. Pine, spruce, and larch provided the best combination of high power output and rapid heating, making them the most suitable fuels for the proposed system. An important advantage of the developed system is its simple design without high-pressure operation of precision turbine blades, which reduce manufacturing cost and improves suitability for autonomous field applications. Compared with the thermoelectric generators and piston heat pipe systems, the proposed solution offers comparable efficiency with a simpler and more reliable design. To validate the theoretical model, a physical experimental setup was developed and tested. The closed heat paper was made of AISI 304 stainless steel with a diameter of 50 mm, vertical section 0.5 meter long, and horizontal section 0.2 meter long. The system contained 0.45 long of distillate water and 0.05 liter of transformed oil under a vacuum pressure of 12.5 kilopascal. The conical 6-blade Onipco type turbine has blade 50 mm long, covering about 50% of the pipe cross-sectional area. Experimental testing confirmed stable system operation. At a thermal power of 2 kilowatt, heating temperature of 140 degrees Celsius, and cooling temperature of 10 degrees Celsius. The turbine reached 380 RPM, while the generator produced 5.8 volt and 50 watt of electrical power. Several limitations were identified, including oil migration, non-uniform temperature distribution, and pressure pulsation during start-up. However, the issues can be resolved through future design improvements and optimization. The results confirm the feasibility and practical applicability of the proposed steam droplet power generation system. The proposed system offers several significant advantages over existing analogies. The Onipco-type conical turbine provides smooth steam expression, reducing flow separation and improving kinetic energy extraction. The construction is simple, uses widely unavailable materials, and does not require high precision machining. The system operating on biomass, a renewable and accessible fuel source. Compared with thermoelectric generators, 3-5 efficiency percent, and piston heat pipes below 3%, the proposed system achieves comparable efficiency with a much simpler mechanical design. Potential applications include decentralized micro power plants, mobile generators, emergency backup systems, and autonomous off-grid energy supply. In conclusion, I would like to highlight 4 key outcomes of our work. First, we have for the first time combined a closed vacuum heat pipe with a conical Onipco type hydro turbine for direct thermal to mechanical energy conversion. Second, we have developed a comprehensive calculation methodology that covers the entire energy transformation chain, from fuel combustion to generator output. Third, we experimentally compute the generation of 50 watt of electricity at a temperature of 140 degrees Celsius, validating the effectiveness of our approach. Fourth, the identified limitations are technically solvable through improved capillary network design and thermal insulation. Thank you for your attention. I am happy to answer any questions you may have.
Any question in the audience? Okay.
I have a question. How does the introduction of finally dispersed water droplets into a stream flow affect the overall thermodynamic efficiency of the power cycle compared to the traditional dry steam systems?
Thank you for your question. The proposed steam droplet system is optimized for operating with low-grade heat up to 140 degrees Celsius, whereas a dry steam mode would require significantly higher operating temperatures or more complex superheating systems to achieve similar efficiency. Because fine droplets in the steam droplet mode significantly alter the thermodynamics of the energy cycle compared to traditional dry steam, as they increase the overall density and heat capacity of the steam flow. This increases the efficiency of heat transfer from the heat source to the turbine. The main allowed vacuum of 12.5 kilopascal, the working fluid, distillate water, begins to evaporate intensively at much low temperatures at atmospheric pressure. This allows for efficient operating with water heating to 90 degrees Celsius just 7 minutes after the furnace is started. A dry steam mode, however, requires complete evaporation of the liquid and subsequent superheating of the steam, which at standard pressure requires temperatures of 100 degrees Celsius and above, and in industrial cycles, significantly higher temperatures. The use of a conical turbine of the ONIPCO rotor type allows for the maximum extraction of kinetic energy specialty from the steam droplet mixture, thanks to a smooth change in cross section and a reduction in turbulence. In a traditional blade system, this would lead to erosion of the turbine blades and a loss of efficiency.
Thank you. Thank you. Dmitro, please.
I have one more question. What are the primary control challenges in maintaining a stable stream droplet ratio for consistent power output, particularly when the system is integrated into industrial microgrid with fluctuating energy demands?
Thank you for your question. In our work, the proposed system, rapid thermal regulation via heat dissipation through a cooling coil, and slow thermal regulation via control of the fuel quantity of the furnace employed to maintain a stable vapor-to-droplet ratio and ensure a stable electrical output. This is done to simplify the design as much as possible. However, the quality of control is rate allowed. First, during startup and when the load changes, pressure pulsation are observed, which negatively affect the stability of power generation. This is due to the inertia of the phase transmission process when the supplied thermal power changes. Because a stable phase ratio is critically dependent of vacuum stability, and any fluctuation in heating temperature due to changes in fuel type and quality alter the intensity of steam generation, requiring repeat regulation of the turbine speed to maintain the output voltage. Our study identified a problem with the flow of oil used to separate the steams, which over time alters the characteristic of the vapor droplets mixture and reduce the output power of the generator system. To minimize these problems, the capillary structure needs to be improved and the full supply automatic.
Thank you. Thank you,
Yeah.
Tatiana. Any questions? Okay, we continue. The next presentation by Kirill Degtyaryov, Marina Чугай, Vasil Gnitko, Denis Kryuchenko, Елена Strelnikova. Durability assessment of power machinery units with track-like defects. One moment.
Dear colleagues, dear chairman, first of all, it is a pleasure to be a participant of such important international event. So, I am Elena Strelnikova from Pithorny Institute of Power Machines and Systems, and I present the paper Durability Assessment of Kaplan turbine shafts with crack-like defects. Here you can see contents of this report. After introduction, I say about research methodology, including basic equation for crack propagation analysis and hypersingular integral equations in model crack analysis. Then I say about numerical results and discussion, including benchmark tests and analysis of crack propagation in Kaplan turbine shafts, and then about conclusion and future. The aim of the study is to develop a robust methodology for predicting the effective life of structural components subjected to cyclic tension, compression, loading. The stress-strain distribution is determined using a coupled finite and boundary element approach, enabling accurate identification of the critical high-stress regions where model cracks will be introduced for further analysis. Crack propagation is evaluated by computing stress intensity factors within a hypersingular integral equation framework. The novelty of this work lies in the application of hypersingular integral formulation to fatigue assessment in both simplified test cases and practical engineering problems. Statistical data on publicity reported Kaplan turbine shafts failure indicates that much events are rarer compared with blade pitch mechanism. Statistical analysis shows that most documented cases are associated with high cycle fatigue under low nominal stresses, or with corrosion fatigue mechanism where corrosion significantly accelerates crack initiation and growth. Here you can see the Kaplan turbine shaft. Now about basic equation for crack propagation analysis. Stress concentrations can initiate cracks in highly loaded regions of a structural element. A two-stage methodology is employed to assess their effects. First, the stress-strain state of the intact structure is determined to identify regions of peak stress. The displacement factor U of cracked element is then expressed as a sum presented here by equation number 1, where U sub 0 denotes the displacement field that would arise in a crack-free structural element subjected to the same external. The field is obtained by solving the following mixed boundary value problem presented here by equations number 2. Here, sigma is the stress tension defined by equation number 3, and epsilon is the deformation tensor. Similarly, the perturbation displacement field U induced by crack presence satisfies the equilibrium equations presented here by formula 4, and the associated boundary conditions are presented here by formula 5. The last equation in 5 enforces the application of corrective traction minus sigma from U sub 0 multiplied by n along the crack faces. For an unbounded body, the boundary value problem, defined by equations 4 and 5, can be reformatted as a hypersingular boundary integral equation expressed here by formula number 6, where alpha denotes the unknown density function representing the discontinuity in the normal component of the displacement field across the crack surface. For a plane-isolated crack subjected to normal separation, the traction operator reduces to differentiation in the normal direction to the crack surface, and equation 6 accordingly takes the form presented here by equation number 7. And here the integrals in this formula is interpreted in the sense of the following limited value presented here by formula 8. And in friction mechanics, stress intensity factors are the Q parameter describing stress and displacement field near a crack tip, and they are essential for predicting crack propagation and structural failure. For more than one crack, only the stress intensity factor K sub 1 is relieved. Next, the database of representative 2D and 3D crack configurations were created. Here you can see some representative cracks. They are of 2D configuration and also of 3D configuration presented here in the slide. Some benchmark tests were considered. First was the crack starts at the boundary of the computational domain. It is assumed that the structural element is loaded by prescribed external stresses perpendicular to the crack orientation. The problem was reduced to solving the following hypersingular integral equations, and here solid lines represent the analytical solution and the points denote the numerical results. Next benchmark tests are connected with 3D problems and the flat cracks. After determining the zones of maximum stress concentration from the stress-strain analysis of the structural element, representative model cracks are introduced into this region. In this study, the planar cracks with elliptical and rectangular shapes were adopted as model cracks. An elliptical crack in the 3 body subjected to uniaxial tensile stress. Table 1 here presents a comparative overview of the stress intensity factor data obtained using the finite and boundary element method with the analytical solution. For the finite element method, more than 55,000 finite elements were used, whereas the boundary element method employed more than 4,000 and 9,000 boundary elements. The corresponding measures are schematically shown in figures 1a and 1b here. The findings are of notable practical importance because they a quantitative basis for selecting the appropriate number of finite elements and defining the optimal mesh density in both boundary and finite element methods. Next test is concerned with infinite body containing a flat crack in the form of square region. This problem was also solved in paper number 2, where the affine transformation was used to map the domain onto the interior of a unit circle. The solid curve here presents the k from 1 from paper 2, while points represent the present boundary element results. Now we consider the crack propagation in Kaplan-Turbine shafts. Here you can see the model of this shaft and also the finite element discretization. Here are the result of stress-strain state of Kaplan-Turbine shafts without any crack. Micro defects are assumed to exist on the outer shaft surface and are modeled as cracks with negligible initial length. The objective is to estimate the number of cycles required for these micro cracks to reach the degraded region, which is considered as an onset of shaft failure. The fatigue crack growth analysis was performed for a surface crack propagated from a sub 0 equals to 0.5 mm to a sub c equals to 7 mm. Since the crack depth does not exceed 3.5% of the wall thickness, three-dimensional effects are limited, as shown in paper presented here, paper number 12. Next, we use Peres-Erdogan's law to define the number of cycles before failure. A compilation of selected literature data together with experimental results obtained by Ukrainian energy machines is presented in the table below. Here are the material constants for the Peres fatigue crack growth law from different literature sources. And here you can see the fatigue life of surface cracks in the turbine shaft for different initial crack size and Peres exponents. They are here in this table. The analysis of micro defect growth in the turbine shaft shows that the initial crack size is the dominant factor controlling fatigue life. For surface cracks with a sub 0 less than 0.1 mm, Peres law predicts a propagation time up to 29 years, depending on the Peres exponent, to reach the critical corrosion affected zone under operational stress presented here. That suggested that early micro defects were extremely small and crack growth was limited by low effective stress. Under conditions of full load operation, a small crack reaches the corrosion zone in approximately 1 year, whereas for partial load operation, this extends to 2-3 years. Conclusion. Analysis of Kaplan-Turbine shaft failure statistics showed that such failures, also rare, are primarily associated with the presence of corrosion-affected zones. This study examines a Kaplan-Turbine shaft with a pronounced corrosion-damaged region detected by ultrasonic testing to evaluate the durability of the life extension after more than 50 years of operation in a hydroelectric power plant. The result demonstrated the possibility for operational life extension beyond 50 years exploitation. Future work will extend the methodology to a broader range of structural components and more complex crack geometries. The authors wish to sincerely thank our colleagues at Ukrainian Power Machines plant for their invaluable support and fruitful collaboration.
Thank you. Are there any questions? Do you hear me? Okay. I have a question. Tell me, please, how significant is the correct initiation phase for this class of low stress, high cycle corrosion fatigue loading of the part? Do you hear me? Is there sound? We have sound? No.
We hear you.
Да. Кирилл Дегтярев, Марина Чурай, Василий Нитко, Денис Криченко, Елена Стрельникова. Are you online?
I saw Strelnikova. It seems for me. Olena Strelnikova, do you hear us? Olena Strelnikova is in conference. Okay, we move ahead. The next presentation, justification of an interdisciplinary educational model for automation engineering students, concept of a laboratory.
Olena Strelnikova, do you hear us?
Yes, I'm here. I'm here. You. Yes, I'm here.
We have question for you.
I repeat my question. Tell me, please, how significant is the crack initiation phase for this class of low stress, high cycle corrosion fatigue loading of the part?
Thank you for your question. It is really very, very important because the correct initiation, we can see slide number 12, that namely initial size is the important factor because the time for fatigue will be considered up to 29 years from 1 year, and it is very important factor. Yes, really. Thank you for your question.
Thank you. Dmitro, please.
I have one more question. Did you consider that turbine blades experience multi-axial stress states, temperature gradients, and variable amplitude loading?
Oh, thank you for your very interesting question. This is the history of this paper. The first variant contained two elements, namely a turbine shaft and the turbine blade. And then after the reviewer comments, they are proposed us to consider only one element. And so we we consider only shaft, but it is our future research. We are going to consider namely a blade of the turbine, and all factors you mentioned are very important. And now we consider all of them without temperature. We are going to consider the temperature field also. Thank you again for your question.
Thank you, Elena. So we can continue our work, and next presentation by Evgen Potapenko, Alina Kazurova, Igor Orlovsky, Evgenia Vasilieva, and Sergei Diev. Justification of an interdisciplinary educational model for automation engineering students. Concept of a laboratory stand as a practice-oriented learning tool. Just a second.
Hello, colleagues. My name is Yevhen Potapenko from the Department of Electrical Engineering at Zaporizhia Polytechnic National University. Today, I will present the results of our research titled Justification of an Interdisciplinary Educational Model for Automation Engineering Students, Concept of a Laboratory Stand as a Practice-Oriented Learning Tool. In Ukraine, the quality of higher education is increasingly measured by graduate employment rates. In universities whose graduates cannot find jobs in their professional field may even lose part of their public funding. At the same time, the labor market, especially in automation and electrical engineering, faces a shortage of qualified specialists. This situation clearly demonstrates a gap between academic training and real industrial needs. Our study aims to bridge this gap through an interdisciplinary, practice-oriented educational model. The traditional university curricula often separate subjects such as electrical engineering, automation, and programming. As a result, students obtain fragmented knowledge and lack the ability to integrate theory into practice. However, modern industry requires engineers who can design, program, and configure complete automated systems, not just parts of them. Therefore, an integrated approach is necessary to ensure that graduates are ready for the complexity of real-world industrial systems. The main goal of our work is to justify the concept of an interdisciplinary educational model that combines electrical engineering, automation and control systems, PLC programming, CAD/CAD design, elements of engineering, pedagogy, and project management. The practical foundation of this model is a laboratory stand design that allows students to design, program, and test real automation systems in one continuous process. We began by analyzing existing teaching approaches used in engineering education. This include project-based learning, problem-based learning, interactive simulating, hands-on laboratory learning, and blended learning. Each of them has advantages and limitations. Project-based learning develops teamwork and problem-solving but requires measured resources. Simulation offers flexibility but lacks realism. Hands-on learning provides real experience but needs costly equipment. Our conclusion is that a combination of these methods, supported by modern digital tools, gives the best results. This combination forms the methodological basis of our proposed module. The module integrates knowledge horizontally across disciplines. Students go through 3 sequential phases, which correspond to the full development cycle of an automation project. Design phase, creating the electrical diagram using ePlan Electric P8. Programming and simulation phase, developing and testing control logic in TIA Portal and PLC SIM. Implementation phase, assembling and testing the system on the laboratory stand based on Siemens S7-1200, Synamics drive, and HMI panel. This structure allows students to move from virtual design to real implementation step by step. The laboratory stand we are developing serves as a reconfigurable training platform for automation tasks such as electric motor control. It includes a 3-phase induction motor, PLC Siemens S7, Synamics frequency converter, HMI panel, and full safety and protection elements. Students can experiment with both relay contactor and PLC-based control schemes, observe system behavior, and debug their programs in real time. The stand is directly linked to a plant schematics, ensuring industrial-grade documentation. The interdisciplinary learning process consists of 6 stages: theoretical preparation, lectures, online courses, system design, circuit development in a plan, programming, creating PLC code in TIA portal, simulating, modeling, testing and debugging virtually, engineering implementation, assembling and testing on the stand, reflection and analysis, reporting and presentation of results. This sequence transforms the instructor's role from a lecturer to an engineering mentor, guiding the students through a full professional project. The module ensures outcomes on 3 levels: knowledge, understanding system design principles and component operation; skills, creating electrical schematics, programming PLCs, and running simulations; competencies, solving real engineering problems, working in teams, and adapting to industrial technologies. Assessment is balanced across 5 components: design, programming, simulation, documentation, and oral defense. Our model is fully aligned with the Ukrainian higher education standards for specialty G7, automation, computer integrated technologies, and robotics. It also reflects the principles of the national STEAM education concept and the European qualification framework, such as interdisciplinarity, systems thinking, learning by doing, digital integration, workforce readiness. At the same time, it directly addresses the labor market demand for skills in PLC programming, SCADA configuration, and CAD documentation. We believe this approach can significantly enhance the quality and relevance of technical education in Ukraine and beyond. The proposed interdisciplinary approach offers several advantages. It replaces fragment learning with systematic engineering thinking. It increases student motivation through visible practical results. It prepares graduates for real industrial conditions and enhances their employability. It provides a flexible framework adaptable to various levels of equipment, from virtual simulation to full physical stands. In the short term, the module will be implemented in virtual format using simulation tools. In the medium terms, a physical laboratory stand will be introduced for blended learning. In the long term, we plan to expand the system toward Industry 4 technologies, digital twins, IoT, integration, and remote access. We also see potential for developing academic industrial partnerships, launching engineering startups with educational programs, and publishing further research in Scopus indexed journals. Thank you for your attention.
Olena Nazarova, please, your question. Turn on microphone, please, Olena.
Okay, sorry. Explain, please, your view about how easy to adopt your educational model and laboratory stand to universities with more limited technical resources.
Thank you for your question. Can you hear me?
Yes.
Thank you for your question. Our model was specially designed to be flexible and scalable, so it can also be implemented in universities with limited resources. The key idea is that educational process can begin in a completely virtual format. Students can use just TIA portal, PLC sim, and simulation software without requiring expensive physical equipment. The first stage is its theory, circuit design, programming, and simulation. Later, when funding becomes available, the university can gradually add physical components. First, it can be a PLC, then HMI panel, for example. Later, frequency converter or sensors, different kind of sensors. This phased approach makes implementation much more realistic for universities with limited budgets. So overall, the model is highly adaptable and can provide quality engineering education even with minimal laboratory resources.
Thank you. Thank you. Dmytro Kulagin, please.
Thank you. Can this laboratory setup be extended to other types of automation tasks or systems?
Thank you for your question. Yes, of course, definitely. The laboratory stand, as I told, was designed as a flexible and reconfigurable platform, so it can be adopted to many other automation tasks, not only motor control. At the current stage, students work just with PLC-based control or of an induction motor. But in the future, the system can be expanded toward Industry 4.0 technologies. For example, we can add different sensors such as temperature sensor, vibration sensor, and collect real-time data using industrial protocols. Then this data can be connected to SCADA or cloud platforms. And another important direction is the creation of a digital twin using MATLAB Simulink. This also allows students to simulate the test systems virtually before working with real hardware. Finally, we come to remote access and maybe AI-based analytics can be added for predictive maintenance and smart diagnostics. That's all.
Thank you. Thank you. Dear colleagues, we are confidently moving towards completing the work of our section, and their final presentation by Igor Maslov and Dmytro Kulagin, identification and quantification of critical energy dissipation pathways within integrated AC architecture of autonomous power units. Second, please.
Good day. Let me present our article titled Identification and Quantification of Critical Energy Dissipation Pathways within Integrated AC Architectures of Autonomous Power Units. Relevance of the issue. The rigorous articulation of the research problem constitutes a pivotal phase in the advancement of autonomous energy systems engineering. A precise and logically structured problem statement serves to delineate the research object, the subject of inquiry, and the anticipated scientific contribution. Within the domain of autonomous power units, a singular technical challenge may permit diverse conceptual formulations, each necessitating distinct analytical methodologies. Conversely, an ambiguous substantiation of research objectives impedes the realization of the core scientific hypothesis and fails to demonstrate the requisite methodological sophistication. Ultimately, the clarity of the problem definition serves as a benchmark for the scientific maturity and technical proficiency required to address complex energy distribution paradigms. Problem statement. The electrical architecture of an autonomous power unit is defined as an integrated complex of electrotechnical installations engineered for the transformation, transmission, and distribution of energy. Its fundamental functional objective is the stabilization of the system's primary electrical drives to ensure operational continuity. The energy infrastructure of a modern autonomous power unit must adhere to rigorous benchmarks of reliability, thermodynamic efficiency, functional safety, and modular scalability to facilitate future systemic upgrades. A primary challenge in the advancement of autonomous power unit electrical distribution is the minimization of active energy dissipation during transmission. The propagation of electrical energy through autonomous maritime networks is intrinsically coupled with complex electromagnetic and thermal processes within subsystem components and technical hardware. The classification of energy expenditure throughout the system lifecycle is categorized into two fundamental components: primary dissipation derived from nominal operational cycles and optimized systemic parameters, and ancillary dissipation resulting from nonlinear load parameters, transient states, and deviations from prescribed operational setpoints. Ancillary inefficiencies are further subdivided into groups based on their causal mechanisms, which include structural inadequacies of the autonomous power unit power grid, the transmission of reactive power across systemic elements, and the suboptimal management of technological processes. The structural optimization of the autonomous power unit energy consumption necessitates a high-fidelity design approach that integrates energy-saving variables into the core logic of the distribution system. Critical design interventions include the precision selection of transformer capacities, the strategic spatial deployment of life support and emergency power nodes, and the optimization of conductor topologies and circuit configurations. The transmission of reactive power through the resistive inductive elements of the autonomous power unit electrical system induces significant parasitic energy consumption. Increased reactive flux precipitates deleterious phenomena, including the reduction of transmission line and transformer throughput capacity and the destabilization of voltage levels. To mitigate these effects, multi-standard optimization strategies for reactive power compensation must be implemented. These strategies focus on reducing the reactive power demand of individual consumers through technical optimization and implementing automated load regulation, such as no-load disconnection protocols for asynchronous motors. Furthermore, transformer optimization requires reconfiguring or de-energizing units operating at less than 30% of their rated capacity. Purpose and objectives of the study. The fundamental objective of this research is to establish the conceptual principles for the development of highly energy-efficient electrical systems within autonomous power units. To facilitate the realization of this objective, the following investigative procedures were undertaken. First, a comprehensive analysis of contemporary methodological approaches concerning the integration of energy-efficient electrical architectures for autonomous power units was performed. This stage focused on delineating the systemic requirements for minimizing dissipation and enhancing operational stability within self-sustained maritime grids. Second, the study identified and evaluated specialized metrics and analytical frameworks required to quantify the energy efficiency of autonomous power unit electrical systems. This involves establishing performance indicators that account for the stochastic nature of autonomous operational cycles and the efficiency of energy conversion and distribution subsystems. Types of energy losses in a unified AC power system. The transmission of electrical energy through the integrated networks of an autonomous power unit is inherently associated with the dissipation of active power. Total energy dissipation is bifurcated into two primary dimensions: fundamental losses, which are dictated by nominal operational cycles, and supplemental losses, which arise from deviations in operational modes. The secondary component of energy dissipation is multidimensional and can be categorized into several distinct vectors. These include structural and architectural imperfections, the parasitic transmission of reactive power, and the lack of optimization in technological processes. Furthermore, energy efficiency is significantly compromised by the degradation of power quality and broader organizational deficiencies in the management of the power grid. The unified energy architecture of an autonomous power unit establishes a consolidated power supply framework by integrating propulsion drive installations with general electrical distribution systems. Mitigating losses requires a comprehensive engineering approach focused on optimizing the quantity and capacity of electrotechnical hardware, the strategic spatial positioning of generation sources, and the synthesis of an optimized circuit topology. Principles of designing an energy-efficient, unified AC power system. The imperative for minimizing energy consumption necessitates a unified maritime energy architecture that integrates fundamental management principles with robust mathematical and economic models. Systemic efficiency is evaluated through the productivity of propulsion installations and the distribution efficiency of power flows, satisfying 5 core criteria: reliability, economic viability, safety, operational simplicity, and continuity of supply. Analytically, the system is partitioned into 3 functional fragments: power supply sources, the distribution network, and individual consumer circuits. This division facilitates a granular assessment of energy transfer efficiency based on system voltage and auxiliary installations. While mainline schemes offer reduced capital expenditure, radial configurations are prioritized for mission-critical loads due to their enhanced reliability. The design theory for complex technical entities relies heavily on the principles of decomposition and hierarchical description. This methodology necessitates the partitioning of the system into distinct levels. By applying these principles, an energy efficiency model can be constructed by subdividing the power system into specific subsystems, including individual power consumers, distribution points, electrical distribution networks, the main switchboard, and the generator system busbars. To evaluate the effectiveness of the proposed hierarchical decomposition method, it was compared with the conventional lumped parameter energy audit approach. Traditional methods treat the autonomous power unit as a consolidated system, focusing on total fuel-to-energy conversion efficiency. In contrast, the proposed method provides the spatial resolution necessary to quantify losses at each stage, from generator buses to individual consumers. Practical application: Icebreaker Kapitan Belousov. The practical application of the proposed hierarchical decomposition methodology is demonstrated through the modernization of the power system of the diesel-electric icebreaker Kapitan Belousov. Given the vessel's specific operational profile, the primary focus is placed on optimizing the propulsion system and auxiliary power circuits. Calculations indicate that increasing the power factor from a baseline of 0.72 to a target of 0.94 for the main propulsion motors reduces the rated current in the main cables by 23.4%. This results in a reduction of active energy losses by up to 18.6 kilowatt-hours per hour of operation at peak loads. Furthermore, implementing sensors to automatically disconnect asynchronous auxiliary motors during periods of low demand eliminates no-load losses, which account for 4.5 to 7% of the total energy consumption of the auxiliary grid. Finally, for the Kapitan Belousov, a strategic replacement of underloaded induction machines with high-efficiency IE3 or IE4 class motors is recommended. This modernization provides direct fuel savings of approximately 3.2 to 4.1 kilograms per hour per unit. Conclusions: the fundamental principle for evaluating the energy efficiency of autonomous power units is rooted in a systematic energy audit methodology, which centers on the granular analysis of individual electrotechnical components. This framework is essential for establishing a comprehensive energy balance and identifying specific dissipation pathways. The scientific novelty lies in the development of an adaptive hierarchical decomposition algorithm, which integrates mathematical models of dynamic processes with economic evaluation criteria tailored for autonomous marine microgrids. Objective comparison confirms that moving from generalized audits to hierarchical analytical decomposition provides a more robust toolset for the structural optimization of autonomous grids. Thank you.
Okay, are there any questions?
I have a question.
Please.
What specific metrics or indicators are used to identify critical energy within the scope of this study, and how do they differ from standard energy consumption measurement?
Thank you for your question. Specific metrics and performance indicators used to identify critical energy within this study focus on granular dissipation pathways rather than aggregate fuel to energy conversion. Key indicators include the quantification of active energy losses across 5-level hierarchy: generator bus bars, first of all, second, main switchboard, third, distribution networks, fourth, distribution points, and fifth, individual consumer circuits. Unlike standard consumption measurements, these metrics account for ancillary dissipation resulting from structural indicators, the transmission of reactive power, and suboptimal load management. Additionally, the study utilized equipment utilization factors such as identifying units operating at less than 35 of their riser capacity and power of factor values to point efficiency.
Thank you, Dmitro. Thank you. I have another questions for you. Tell me, please, what methodology was employed to quantify the identified energy factors, and what are the primary challenges in ensuring the accuracy of these calculations?
Thank you for your question. The methodology employed to quantify energy factors is rooted in a characteristical analytical deconsumption and adaptive algorithms designed for autonomous marine microgrids. This approach partitions to the power system into functional fragments to isolate specific loss pathways during energy transformation and distribution. The primary challenge in ensuring the accuracy of these calculations includes the stochastic nature of autonomous operational circles and the complexity of modeling nonlinear load parameters during transition states. Furthermore, maintaining accuracy requires high fidelity simulation of both statistic and dynamic processes to account for the and create between systemic elements in varying environmental conditions.
Thank you. Thank you.
I would like to ask you about your future research plans in this field.
This research is part of whole researching program of my doctorand Igor Maslov, who's write about this question, his dissertation. And this dissertation works is now in the process. In work process.
Thank you, Dmitro. This was our final presentation in our section. And I would like to thank all participants for their interesting presentation. And thanks to organizer for opportunity to discuss our scientific achievements.
Now we will have 30 minutes break for lunch, and section 3 will start 1 p.m. See you 30 minutes.
See you. Have a nice day. Bye.
Good day depends on stable performance
Good afternoon, dear colleagues, participants, and guests.
Good afternoon, ladies and gentlemen, and welcome to session number 3, Innovative Aerospace Technologies and Unmanned Aerial Vehicles. My name is Yaroslav Virnik, and I'm pleased to co-chair the session alongside Pavlo Trishin and Mikhailo Frolov. Today, we have an excellent lineup of 5 presentations covering advanced UAV routing, edge compute, detection models, and electromagnetic modeling. We will have a question and answer session immediately following each presentation. And let's begin. First, I would like to mention that because of absent some speakers, we'll begin from the third one, Yegor Popov. Please tell me, are you ready? Or Yegor Sopov, I'm sorry.
Yes, good afternoon. Of course, I'm ready.
Okay.
Ladies and gentlemen, esteemed colleagues, allow me to introduce myself. My name is Yegor Sopov, and I'm a postgraduate student at National Aerospace University Kharkiv Aviation Institute. It is an honor to take part in your conference for the second time in a row, and this time I would like to present our research on multi-agent learning methods for UAV swarm routing, focusing on integrity and data freshness, which I've conducted alongside my scientific advisor Alina Artyomova. We got interested in the subject because UAV swarms, as a rule, struggle to maintain the said data freshness and integrity, operating as they do in dynamic and often unreliable environments. Let's begin by exploring why this topic is important in modern applications. UAV swarms are increasingly used for distributed autonomous missions, where several UAVs must coordinate their actions without permanent human control. In such systems, communication is not only a technical layer, but a critical condition for coordination and situational awareness. However, classical FANet routing protocols, including AODV, OLSR, and GPSR, often degrade in UAV swarms. The main reasons are high node mobility, frequent topology changes, strict energy constraints, and cyber-physical threats. Therefore, this article focuses on adaptive routing based on multi-agent reinforcement learning. This study aims to evaluate whether multi-agent reinforcement learning can improve UAV swarm routing under both normal and adverse conditions. To achieve this, routing is represented as a decentralized multi-agent decision process. 3 moral algorithms are trained under the STDE paradigm and compared with classical FANet baselines across different swarm sizes and threat scenarios. Our evaluation workflow combines Capella-SIEM, NS3, and MATLAB. Capella-SIEM provides UAV mobility traces, NS3 performs packet-level evaluation, while MATLAB is used for statistical aggregation and visualization. The architecture follows the centralized training with decentralized execution paradigm. During training, the critic or mixing network can use global information, including the global state and joint actions. However, during execution, each UAV acts independently, using only local observations. This is important for UAV swarms because a permanent central controller is unrealistic under mobility, limited bandwidth, and possible node failures. The study evaluates 3 representative moral algorithms. MADDPG is an actor-critic method suitable for coordinated multi-agent control. MAPPO is considered because of its stability in cooperative learning tasks. QMIX is especially relevant for routing because next hop selection is naturally a discrete decision. The comparison in this article shows that all 3 methods follow CTDE, but differ in scalability, flexibility, and suitability for discrete routing logic. The experimental workflow combines 3 tools. Capella-SIEM generates UAV mobility traces. These traces are then replayed in NS3 for packet level evaluation. Finally, MATLAB is used for aggregation and plotting. The experiments cover 3 swarm sizes: 10, 20, and 30 UAVs. The evaluation includes benign aberration, intermediate jamming, and a black hole insider. The main metrics are end-to-end delay, throughput, and packet delivery ratio. Under benign conditions, the first clear result is the effect of scaling. As the number of UAVs increases, end-to-end delay grows. This is expected because larger swarms create longer forwarding chains and stronger medium access contention. At the same time, throughput decreases as the network becomes denser. The important point is that the difference between routing methods is smaller than the general scaling trend. In other words, scalability is the dominant factor shaping the QoS envelope. Packet delivery ratio is used as the main proxy for integrity because it reflects whether packets are successfully delivered. The results show that PDR gradually decreases when the swarm size increases. This is typical for dense multi-hop FANETs, where collisions, link breaks, and queue overflows become more frequent. However, model-based routing remains competitive and stays close to the best-performing baseline envelope under stable channel conditions. The intermittent jamming scenario shows a clear downward shift in both throughput and packet delivery ratio. This means that interference affects not only the amount of delivered traffic, but also the reliability of delivery. The effect becomes stronger as the swarm scales, because multi-hop forwarding increases the probability that at least one hop is affected by interference. Model-based routing often remains closer to the higher achievable throughput reliability envelope, because learning-based policies can react to short-term delivery feedback. The black hole scenario demonstrates the effect of malicious packet dropping. Here, the most visible indicator is end-to-end delay, because packets are repeatedly affected by route instability and failed forwarding path. This effect becomes more pronounced in larger swarms, where each packet may depend on more intermediate relays. Overall, the results show that scaling remains the strongest quality of service factor, but model-based routing can better preserve the achievable performance envelope under interference and insider dropping. As a conclusion, let me reiterate the main findings of our work. Centralized training decentralized execution, or CTDE, makes coordinated training feasible while keeping execution fully decentralized. Next, swarm scaling is the dominant driver of delay, throughput, and packet delivery ratio, or PDR. Third, under jamming and insider dropping, model tends to stay closer to the best performing envelope. Our future research will be focused on more complex mobility regimes and variable UAV speeds. We will utilize heterogeneous radios and different UAV classes, and examine stronger threat models like collusion, selective forwarding, and adaptive jamming. The focus of our research will involve lightweight model policies for embedded onboard deployment. We express our sincere gratitude to the university and our department for their support, guidance, and access to simulation platforms. Thank you for your attention. I will now be happy to answer any questions that you may have.
Thank you for your presentation. This was very interesting.
Yeah, thank you for your excellent presentation. Are there any questions from the audience? If not, I'll have several questions for you. The first one, what is the main practical advantage of your approach compared to traditional routing methods?
Thank you for the question. This was actually one of the topics of my presentation at the conference last year. So traditional routing methods such as ad hoc on-demand distance vector or AODV and OLSR, they are very effective in structured networks. But in mobile swarms, they start exhibiting high latency, and they are less energy efficient, which is obviously very important for drones. And this can be a bit improved by using geographical protocols, but the results of our work show that the most promising approaches are either swarm intelligence based or reinforcement learning based methods, or combined. Our results show that reinforcement learning based methods outperform other protocols and basically achieve the lowest delay and the highest packet delivery ratio, making it the key to enabling adaptive and robust real-world application methods. So it's like a golden average, the best of both worlds.
Okay, thanks for the answer. And the next question is, how realistic are your simulation results for real-world UAV applications?
Thank you for this question, either. Well, of course, any simulation would be inferior in its credibility compared to real-world results. But unfortunately, in the current conditions with the war going on, we are heavily limited in our abilities to carry out actual experiments using high number of drones. So because of that, we are currently doing experiments in our department's laboratory using lightweight drones. And these drones should confirm our results with a higher degree of certainty. And hopefully I will be able to report on this when we're done. Thank you.
Thank you very much for your presentation. Moving on. And the next presentation, we have a paper on computer vision titled MobileNet version 2 SSD FPN Lite model in unmanned aerial vehicles detection tasks. Presented by Oleg Zaritsky. Oleg Zaritsky. Okay, the floor is yours. Sure.
Thank you very much.
Разрешение превышает на секунду. Что ж такое? Sorry for some inconvenience. Please wait.
Good day, dear colleagues. Today we are going to talk about light neural networks in unmanned aerial vehicle detection task based on MobileNet. I divided my presentation into some parts, and let's start from introduction and just have a short look at the main challenges. I don't pay a lot of attention on abstract. You can find it in my paper, but I like to mention that study proposed and investigated balance model architecture for detecting major strike and reconnaissance unmanned aerial vehicles with a focus on Shahed UAV, because this type of drones strike the most in the world, and we have the biggest disaster for the civilian people and for critical infrastructure. The research confirm the problematic existing problematic aspects of that network in terms of detecting small objects in images, but by introducing additional layers that receive features from the early layers of the base network and form a feature map for detection, it was possible to obtain a high level of mean average precision indicators on the level about 96% and balance F1 score it's more a little bit more than 80%. There is some insights. The research also revealed unexpected result regarding the slight increase in model performance after the quantization process, and I tell about this a bit later. Some word about relevance of this research. Of course, I hope that everybody understand the importance of this topic, how to detect, how to track unmanned aerial vehicles. I mean, strike and reconnaissance. You can see infographic for this slide. It's about military drone market dynamics. And of course, the global military drones market is estimated to be it's $15 billion in 1995 and is predicted to reach more than 22 billions in 2030. The same picture we can see on the Middle East, of course, and some words about geography. And I don't tell about the Ukraine war, since we know all these statistics, how many people were killed by this drone since the beginning of the invasion of Russia in Ukraine. And I'd like to pay your attention that implementation of this drone expands on different regions, including Europe. You can see this on the slide, and in the war in the Middle East, we can see a lot of the very big number of implementation and using these type of drones in the Middle East. So the relevance of topic is clear, and I'd like to say some words about the main challenges in the task of detecting and intercepting. I put on this slide only 5 of a lot of different challenges, but it's maybe the most relevant. Small radar and thermal footprint. Because of this, no one of the available methods, I mean, it's radar, optics, acoustic, or infrared detection is sufficient on its own, so we need to combine all these different methods in pipeline. Radio electronic silence and fiber optic control, and this fundamentally changes the detection paradigm from passive radio signal interception to active sensor methods. We need to use radar, infrared, acoustics to identify and to detect different type of unmanned aerial vehicles using their sound. And of course, according to the main tactics of using these vehicles in the night time, we need to use infrared cameras, but all these methods are supposed to use computer vision algorithms. So my research was dedicated to this topic. And of course, if we have such a problem or such a challenge, we need to solve this problem. You can see the example of different type of unmanned aerial vehicles that is supposed to use as an interceptor. I just put these photos on this slide just to show the idea and to say that all these drones have a common feature. They all are equipped with the cameras, different type of cameras. It's optical electronics camera and the cameras in infrared range of spectrum, and all these interceptor and features supposed to be fully autonomous. I mean, from the point of view of guidance and tracking system, to help operators to to identify, to detect, and to track animals, unmanned aerial vehicles with the biggest possible efficiency. So the research objectives was to identify the problematic issues in object detection task using neural network models and on edge devices, provide possible recommendation for the formation of effective model architecture to increase accuracy and recall, and study the impact of model quantization on the accuracy during the implementation on edge device. Research methodology, you can see the model's architecture. I'd like to say some words. I try to get the features from different layers and to research different combination. Of course, on the basis of the MobileNet version 2 CCN FPN Lite model. You can see here different ideas about the models that were involved in this research, and you can see two parameters that were changed. I mean alpha and weights. The alpha parameter determines the depth of the model in each layers. It controls how many filters or channels will be used in the convolutional layers. And weights parameters specify whether the model will be initialized from scratch or will be used pre-trained weights, for example, a value of ImageNet or other dataset name indicates that the weights are trained on the large dataset, typically for classification problem. This is used for transfer learning. A value of known means that the model is initialized with random weights. So this is a combination of different models in my research. Very briefly about dataset. Dataset was created within the Rainbow Flow environment and consists of almost 8,000 images, which were used which have the specific size for the MobileNet neural network training, of course. And the dataset or images were classified into 4 principal categories. It was shahed, other UAVs and birds, and the backgrounds. And I need to say that other UAVs include more than 20 different types of unmanned aerial vehicles. And it resulted in some problems, but now I'd like to say that now I divided all these other UAVs in separate classes, and now I'm training my neural network with a data set which includes more than 20 classes. Of course, I used augmentation to increase the quality of training. Very briefly about the result of modeling training. You can see the real the detection of objects here, and it was possible by combining different layers, I mean features from different layers from the lowest layer in the neural network to have the high precision even in when we have a very small object in image. Next slide gives us an imagination about the precision recall and F1 score. It's a basic metrics for such type of training. We can see that model C had the highest accuracy among all previous models, the least false positive, and the best balance between accuracy and the number of errors. And among the shortcomings, it is necessary to highlight the emission of object in image with several classes, whereas a problem is groups of objects of the same class, but is not critical for detecting task name. Shahed has an average recall on a very high level. Model D has high recall, high accuracy, and work effectively with a group of objects in the same class, however, it's not without drawbacks. It has some problems with the classification, confused classes in some complex sense, and has a higher number of false positive compared to other models. This slide includes information, so comparison on different models' performance metrics with the confidence threshold. It's on very low level, but the more interesting information, the size of this model before and after quantization. And you can see that, for example, model I, its original model, it's about 33 megabytes. And after transferring into a using the different type of the number of digit in weights of this model, we got the model size is about 3 megabyte, and the model C, for example, even it's about 1 megabyte per 0.2. So it models, the size of these models allows us to implement this model on the edge device and use on the board or our unmanned aerial vehicle that we can use as an interceptor. So basic conclusion, model A demonstrates the best balance and can be recommended for most object detection tasks. In general, we can say that all models, so A, B, C, D, and E, show consistently high quality and performance in all scenarios and can be described as full of high quality or universal model. It's a model A and D, and high accuracy at model C. It should be also noted that there are general problems that remain inherent in almost each of the models to a greater or less extent, including error in class separation, problems with detection on low contrast images, systematic problem localization, and difficulties with the detection on contrast images with many classes. From the point of view of the model architecture, it is necessary to further investigate how the addition of layers 2 or 3, which are responsible for the formation of texture and shapes, will affect the quality of detection. And I think that it can positively affect the detection of the object in overload scene. According to the training result, model I is universal and the most productive, but has the potential to increase its performance after improvement to solve the identified problems in both the architectural and algorithmic parts. For example, after increasing the methods of augmentation from 6 to 12 and testing the different parameters on the loss function, leads to a significant increase in accuracy. It's about 97%, and which after quantization remains at the level of 92%. Somewhat about can be seen before from the transformation result. The models were significantly reduced in size, which allows them to be deployed on controllers. But there is another interesting details that I have mentioned at the beginning of our presentation that indicates an increase in performance indicators in some classes, especially mean and average precision. This is very interesting and not so rare observation when the in-tate quantization activity light model after transformation even shows better metrics than the original floats version. And the main reason is when going from the 22 to 8 digits, the dynamic range of the weights is limited. This is actually like regularization by discretization. And the models loses excessive sensitivity to small changes in the inputs and weights, and as a result, overfit is reduced. So the smallest version is not only lighter, but also behaves like a model with better regularization. So thank you very much for your attention. So I'm open for your question. Good day, dear colleagues. Today we are going to talk about light neural networks in unmanned aerial vehicle detection task based on MobileNet.
So, thank you for your presentation.
And
Are there any questions in the audience?
May I have one?
Of course.
I just wonder if, thank you, by the way, thank you for your report. And I just wonder if your report, to what extent your report contains, let's say, sensitive information.
Yes, thank you very much for your question. Of course, there is no sensitive information in my report. It's all information or all images for my data set was taken from open source. Of course, you can find all this information on the internet, so no closed information at all. So it's an answer for your question. Yes.
Thank you.
I see what you mean, but I see what you mean.
Thank you.
Okay, thanks. And one more question is, wait a minute. How well does your model perform in real world conditions such as bad weather or visually complex scene?
This is a very good, very interesting question. This is the biggest problem for all existing approaches, approaches of detection and tracking. But frankly speaking, I am working with real data from camera from different intercept UAVs. And more or less all these scene, all these video describe very clean weather, more or less, sometimes cloudy, but more or less it's a good condition. So actually, the model don't have any troubles in detection task, maybe some troubles with tracking, but if we have some occlusion, some sunlight, directly in the camera, so we have some specific effects, and the precision of detecting could be less than we achieve, of course. But the biggest problem here not the weather condition, the biggest problem the small object, and it's very interesting to make a clear detection when our objects are more or less, in size, maybe 2 or 3 pixels in a common image. So this is the biggest picture to make identification and detection in a very big distance. So thank you very much.
Thank you for your profound investigation, and we are moving on. The next presentation titled Mathematical Models of Waveguide with Narrow Impedance Walls. The authors are Lyudmila Logacheva, Tatiana Bugrova, Natalia Chernoborodova, Mikhail Chernoborodov, and Sergei Marchavka.
Mathematical model of a waveguide with narrow impedance walls carried out by the employees of the Zaporizhia Polytechnic National University, Lyudmila Logacheva, Tatiana Bugrova, it's me, Mikhail Chernoborodov, Natalia Chernoborodova, and Sergei Marchavka, Ukraine. Slide 2. Objective. During the operation of transmitters in radar, space communication, and telecommunication systems, the problem of reducing out-of-band radiation becomes particularly critical, and this is addressed by suppressing unwanted harmonics of the fundamental frequency using specialized absorptive waveguide microwave filters. However, the design of such devices is a non-trivial electrodynamic problem. Despite the availability of a number of specialized surface tools, numerical modeling does not always make it possible to find an optimal design. In such cases, an analytical approach remains the only option. When solving electrodynamics problem related to the propagation of electromagnetic waves along surfaces whose structure and parameters may vary in a complex manner, the method of equivalent boundary conditions by Leontovich is highly effective. Among the advantages of the impedance approach for solving electrodynamic problems is the simplification arising from the fact that the electromagnetic field is determined only outside the surface, where the boundary conditions are applied, while the fields inside the surface are not considered. Thus, the boundary conditions act as an auxiliary construct that significantly simplifies the solution of the problem. So, the objective of research is to develop an analytical model describing the dispersion properties of several coupled waveguides, the primary rectangular waveguide and the secondary circular cross-section waveguides, in order to determine the types of bulk and surface waves propagation in such structure. Model geometry. Figure 1a shows a rectangular waveguide with a non-periodic, in the general case, sequence of coupling AP2S in its narrow walls. And to enable the use of approximate boundary conditions, in Figure 1b, the non-periodic sequence of secondary circular waveguides is replaced by a smooth impedance surface with a uniform isotropic impedance Z sub S. This is a model of an absorptive harmonic filter. The complex structure of this impedance makes it possible to determine the level of attenuation of unwanted harmonics in the primary waveguide. Problem formulation. In the case of TE waves, the longitudinal component of the magnetic field H sub Z is described by the Helmholtz equation 1. The solution to its partial differential equation obtained by the Fourier-Bernoulli method is determined by the values of the unknown coefficients A, B, C, D, and transverse wave numbers gamma sub x along the x and y coordinates. The Leontovich boundary condition 3 make it possible to relate the magnetic field component H to the electric field E. Slide 5. Solution. By applying the Leontovich boundary conditions to the narrow walls of the waveguide 4, the corresponding expression for the longitudinal component 5 of the magnetic field are obtained. Using the relationship between the longitudinal and transverse components 6 for the case of TE waves, the dispersion equation 7 with respect to the transverse wave numbers gamma sub x is derived. After normalizing the impedance and wave numbers to the free space parameters, we consider the case where the impedances of the narrow walls are purely reactive, are lossless. Slide 6. Dispersion equations. We obtained two cases of the dispersion equations 7 with respect to the transverse wave number gamma sub x for the bulk wave when gamma sub x is real, and for surface waves when gamma sub x is imaginary. Slide 7, analytical results. We obtained two cases of dispersion equations. 8 for the bulk wave and 9 for the surface wave. Numerical results. For the bulk waves, figure 2 shows the dependence of the phase velocity of bulk wave propagation on the value of the surface impedance. For the frequency range of the second harmonic and above it, the dispersion of the waves is practically absent, and the velocity practically does not depend on the resistance of the transition hole. Dispersion differences appears in the frequency range below the second harmonic, where there is dependence both on the resistance value and on the frequency. For magnitude of z sub s less than minus 0.3 g, a rapid increase in the phase velocity of the bulk wave is observed, which quickly begins to slow down with an increase in magnitude of z sub s for a fixed frequency. The more zs approaches 0, the more the normalized value of beta approaches its value in an empty waveguide. Numerical results for the surface waves. Figure 3 shows similar frequency dependencies of the propagation constants of two surface waves. In contrast to the identical behavior of bulk waves, surface waves demonstrate a different propagation character, and the three propagation characters can be distinguished. At magnitude of z sub s is equal to minus 2j, one surface wave demonstrates a weak anomalous dispersion. With increasing frequency, the propagation constant beta decreases. And for the second wave, under the same conditions, a symmetric weak normal dispersion is observed. Thus, with increasing frequency to 1.8, the dispersion differences of both waves decrease, and further, the two surface waves transform into one. With increasing resistance, this symmetry disappears, and the dispersion character becomes the same for the both waves. Thus, at the magnitude of z sub s is equal minus 5g, both surface waves we have a weak anomalous dispersion, and the value of the propagation constant continuously decreases with increasing frequency, without crossing the straight line beta divided by k sub 0 to a unit. At large values of the impedance of resistance in the region of the first harmonic of the frequency, exclusively bulk waves arise. The nature of propagation of both waves is characterized by normal dispersion. But at the moment of crossing the straight line of unit, one of the bulk waves turns into a surface wave. The second one remains bulk. Slide 10. Conclusion 1. The problem of diffraction of the fundamental wave at the impedance jump of a narrow wall of a rectangular waveguide is solved by applying the Lentovich impedance method. 2. A mathematical model of electromagnetic coupling of waveguides of rectangular and circular cross-sections through a circular hole in a narrow wall is constructed. 3. Two types of transcendental equations are obtained for finding propagation constants for two types of waves, bulk and surface. Strong dispersion is observed in the frequency range up to the second harmonic only for the bulk wave. In this range, the value of the propagation constant decreases with increasing frequency, which corresponds to anomalous dispersion. Slide 11. Conclusion 4. The analytical model allows for a throughout and computationally efficient modeling of electromagnetic phenomena occurring in directional structures in the decimeter, millimeter, and submillimeter wavelength ranges. 5. The proposed approach can be applied to the analysis of complex structures, band and notch filters, directional couplers, dividers of phased antenna arrays, and so on, that are used as the main elements of microwave technology. This approach allows for a analysis of the electromagnetic field distribution in both single-mode and multi-mode propagation modes. Thank you for your attention.
Thank you for your presentation. I now open the floor for questions. If there are any questions for the speaker? Okay. Mikhailo?
Yes, okay. I have one. Thank you for your presentation. And as far as I'm concerned, you presented the results of numerical simulation in your report. It's interesting. Have you made some validation of your models?
We have no experiments, and the validation of our method may be done with the comparison of classical waveguide problems by other results by other authors.
Okay. Okay, thank you.
Okay, and one more question, please. How accurate is the Leontovich impedance boundary condition for modeling real waveguide walls with complex geometries? And under what condition does this approximation start to break down?
The limitation of the methods is the condition where the locally flat approximation stops working, the flat approximation.
Okay, thank you. Thank you very much. And let's move on to our first two presentations. And I would like to ask, is anybody responsible for the first presentation, titled "And Integrated Frequency Analysis and Trustworthy Cloud Deployment"? Okay, I see we don't have here the authors of these investigations. We just let me to show this presentation. And the first one is an integrated frequency analysis algorithm of UAV road planning metrics incorporating Irwin criterion-based anomaly filtering.
Автор Егор Артемов, Sergey Popov, Alina Artemova, and Artemy Artemov.
Good day, dear colleagues. My name is Igor Artemov, and I'm glad to be here today to present my report titled "An Integrated Frequency Analysis Algorithm for UAV Road Planning Metrics Incorporating Irwin Criterion-Based Anomaly Filtering." UAV route planning is a complex multi-criteria problem that requires the integration of classical, intelligent, and statistical methods. Effective planning depends on stable performance metrics such as energy consumption, mission duration, route length, coverage efficiency, and safety constraints. Existing approach often consider these methods separately and fail to account for parameter fluctuation, UAV heterogeneity, and short missions, which may lead to unreliable evaluations. The contribution of researchers in this field are summarized in table. This work aims to develop an integrated frequency analysis algorithm for UAV route planning metrics with anomaly filtering based on the Irwin criterion. To ensure the universality of UAV route evaluation for different aircraft types and missions, a modified Irwin criterion is proposed. Unlike the classical approach, it accounts for heterogeneous data and preserves natural parameters fluctuations typical for short routes. The methods enable reliable detection of anomalies, support multi-parameter analysis, and maintains flexibility for incorporating additional factors. UAV route efficiency is evaluated using key indicators grouped into 5 categories: planning efficiency, reliability, mission success, safety, and energy efficiency. After normalization and anomaly filtering, the indicators are aggregated to compute overall route performance, as illustrated in the proposed algorithm. The calculation is performed for each route variant, using a set of normalized indicators covering different aspects of mission performance. All indicators are adjusted to a common optimization direction to ensure correct aggregation. Group-level indicators are then computed by averaging normalized values within each functional group, resulting in performance score in the range between 0 and 1. These values reflect the quality of each route depending on the optimization criteria. The proposed approach ensures standardized processing of heterogeneous data, reduces the impact of anomalies, and provides clear interpretation at the group level. It is scalable and suitable for real-time UAV application without requiring large training datasets. The resulting group performance indicators are summarized in table. Spectral analysis based on Fourier methods is applied to study the dynamic of key UAV flight parameters, including energy consumption, speed, and altitude. Using average time series with removed trends allows accurate identification of periodic components. Flight parameter variation can be represented as a sinusoidal harmonics, where a limited number of harmonics ensures sufficient accuracy without over-complicating the model. This enables the detection of cyclic patterns and improves the reliability of route optimization. The aggregation of group performance indicators provides a compact and multidimensional representation of route efficiency, reducing the influence of random fluctuations and supporting route ranking. To enhance accuracy, the discrete Fourier transform is integrated directly into two evaluation processes, enabling effective analysis of dynamic properties within the route planning methodology. In UAV route optimization, the dynamics of key flight parameters such as energy consumption, speed, altitude, and controllability are analyzed using Fourier methods. This approach represents periodic variation as a sum of harmonics. The flight parameter is approximated by a Fourier series where coefficients define the amplitude and phase of the fundamental harmonic and are estimated using the least square methods. Discrete observation points are used to capture parameter behavior over time, allowing consideration of local fluctuation and trends during flight. After coefficient estimation, trend removal is performed to isolate a meaningful variation, and the obtained coefficients are used in the route optimization model. Using the calculated first harmonic coefficient, the Fourier equation describes the main periodic behavior of UAV flight parameter around their mean value. This approach provides sufficient accuracy while maintaining model simplicity, which is important for route optimization. To verify the presence of more complex dynamics, a second harmonic was also analyzed. However, comparison with experimental data shows that it does not significantly improve approximation accuracy. Therefore, the first harmonic is sufficient for modeling parameter variation, reducing computations complexity without loss of accuracy. Additionally, route optimality is assessed using geometric analysis of parameter curves, where the area under the curves reflects the influence of different factors of the route efficiency. In this study, parameter variations are evaluated using geometric analysis where areas under the curves are calculated. This allows quantitative assessment of the influence of flight parameters on route efficiency. A comparison of optimal routes with and without harmonic consideration shows that the first harmonic provides sufficient accuracy for most parameters. The Fourier method effectively captures periodic variation, improving the reliability of parameter evaluation without significantly changing route selection. Overall, geometric and harmonic analysis support accurate and efficient identification of optimal UAV flight trajectories. The proposed integrated frequency analysis algorithm enables reliable evaluation of UAV flight parameter dynamics, while the modified Irwin criterion improves the robustness of route metrics. The results show that the first harmonic is sufficient for accurate prediction and route optimization, whereas additional harmonics do not provide significant improvement. Harmonic analysis enhances the identification of stable and efficient trajectories, leading to reduced energy consumption and improved flight reliability. The study is based on a limited dataset, and further validation using real flight data and advanced simulation is required. Future work will focus on multi-factor models and adaptive real-time route predictions. Thank you for your attention.
Okay, thank you for your presentation. If we don't have here responsible for this presentation, we'll move on to the next one. And the theme of the next investigation is trustworthy MEC cloud deployment optimization for UAV swarms in critical monitoring. Authors Bogdan Kosarevsky and Artem Tetsky.
Hello, colleagues. I'm Bogdan Kosarevsky, and I will present joint work with Artem Tetsky from the National Aerospace University Kharkiv Aviation Institute. Our topic is trustworthy mobile edge cloud deployment optimization for UAV swarms in critical monitoring, where delay and packet loss aren't only performance metrics but can affect safety and mission outcome. Brief context. UAV swarms for infrastructure monitoring, search and rescue, and asset inspection need low telemetry control latency, typically 10 to about 100 milliseconds, and dependable wireless delivery. A distant centralized cloud stretches path and amplifies delay. Under stress, tail latency P95 and P99 often determines whether the loop stays controllable. Reviews still flag open issues. Swarm mobility, fault tolerance, and trust beyond pure cryptography. NIST ties edge trustworthiness to reproducible configuration, controlled updates, and auditable change, which in practice matches GitOps reconciliation and even driven autoscaling. So, staple of the conversation. In critical monitoring, a failed rollout or Mac outage can cost mission like an SLO miss, so trust belongs in the deployment model from the start, not as an afterthought. Mac cloud placement for UAV swarms was formalized and optimized under the latency, including tail metrics, under cost or energy proxies, and under reliability and trust constraints. The structure of the contribution is fourfold. First, a multi-objective formulation with SLA, capacity, and trust. Second, a two-level solution, offline Pareto search plus online control. Third, an explicit link to operational practice, GitOps cadastyle scaling as part of the model, not just as a footnote. 4, validation through one integrated pipeline, Copilot SIEM, then NS3, then MATLAB on 3 mobility patterns. The model assumes heterogeneous compute nodes split into edge and cloud. Mac gives low access delay but limited capacity. The cloud gives plenty of compute at higher network delay. Tasks are generated by the swarm. Each task is characterized by a workload, a maximum delay from the SLA, and a minimum trust or reliability level, in line with architectural trust guidance for distributed edge systems. Assignment is binary. Each task is mapped to exactly one node. End-to-end delay aggregates communication, processing, and overhead, including cold start and burn time tied to containerized deployment, GitOps driven rollout, and autoscaling. Because the scenario is safety critical, multi-objective optimization was chosen. In the Pareto sense, three groups of criteria are minimized: a tail-oriented latency measure, worst-case style over time, a total cost proxy for edge energy or cost, and a risk or trust term on nodes and links. The criteria wasn't collapsed into a single weighted sum. Instead, a Pareto set was computed so an operator still can choose a point that favors latency or reliability depending on the mission. Constraints cover MAC capacity, per task SLA, and trust thresholds. The decision variables are binary. The problem is mixed integer, multi-objective, and NP-hard, which matches known complexity for MAC placement and reliable offloading. The solution architecture has two stages: offline. NSGA2 was run on scenarios from Capella SIEM mobility plus NS3 metrics. Delay and packet delivery producing a Pareto set of fashionable deployments. That is a precompiled menu of latency cost risk trade-offs, so the full placement problem isn't solved from scratch during the mission. And online. When FANet topology and radio conditions changed, drift plus penalty Lyapunov optimization was applied. Each step, the controller uses queue backlogs, link quality, and trust scores to pick a precompiled Pareto point or a small stabilizing adjustment. That pattern is standard for stochastic network optimization over time varying wireless links. GitOps was not added into simulator. It enters as design principle as a rollout time in the model. A real deployment could choose the loop with GitOps or DevSecOps at the edge declarative traceable changes rather than ad hoc edits. GitOps was not implemented inside the simulator. It was represented as a design principle and explicit time overhead in the model. In a deployed system, the online loop could be enforced through GitOps or DevSecOps pipelines. In the edge, declarative traceable changes instead of ad hoc edits. To see how different UAV mobility patterns affect network performance and reliability, a three-stage simulation pipeline was built. Capella SIEM was used for realistic trajectories, NS3 for network-level reply, and MATLAB for statistical processing of delayed tails. For the experiments, three modules were configured in Capella SIEM. A convoy with 10 UAVs, a grid for area coverage with 20 UAVs, and a high mobility random pattern with 30. Paths were exported to CSV, replayed in NS3, and analyzed in MATLAB. Convoy scenario. Stable geometry, a little routing charm. In NS3, delay was observed in roughly 5-11 milliseconds range. Packet delivery ratio landed around 0.90 and 0.99. So for a compact, calm swarm and baseline Mac deployment with cloud backups was shown to be sufficient. Grid scenario. Larger area and more concurrent traffic. Delay increased to about 6-18 milliseconds. PDR remained high, 0.96, 0.98. Averages still look acceptable, but tail latency becomes the pain point, which supports placing Mac closer in delay critical zones and using queue-aware online control. And twist scenario. Random targets and high mobility drive frequent road trips. Delay spread to roughly 25-45 milliseconds. Over a 10-second window in MATLAB, both P95 and P99 clustered near 45 milliseconds with a very narrow gap. So under congestion, most traffic sees the same bottleneck, tailored scale in a FANet-like network. PDR fell to about 0.8, 0.9, clearly below the grid case. Putting it together, trust-aware placement, offline Pareto planning, drift-loss penalty control, and controlled operational change were all found to matter. Cloud-only placement cannot meet aggressive latency targets unless compute is moved toward this form. To summarize what was delivered, a trust-aware multi-objective model for Mac cloud deployment in UAV swarms under critical monitoring, aligned with NIST on distributed trustworthiness. Offline Pareto plans were produced with NSGA2, online adaptation was handled with Lyapunov drift-loss penalty control. The full chain was validated with Capella SIEM, NS3, and MATLAB on 3 mobility patterns. The main conclusion here. Trustworthiness has to be co-designed with placement and queue control. Under high mobility, neither delay-only optimization nor tooling by themselves closes the gap to mission-grade SLOs. Thank you for your attention. I will be glad to take questions.
Thank you for your profound investigation. And now, that concludes all the presentation of session number 3. And with that, we wrap up today's program. I would like to sincerely thank all speakers for their excellent research and the audience for their attention. That's all.
See you tomorrow.
So thank you, everyone.
On the next section. Goodbye.